Good afternoon, good morning to our attendees of Tech Talk. We're just going to give everyone a few minutes and I will pass the mic over to Mr. Dave Culland. Thanks for joining us.
Yeah, good morning, good afternoon, everyone, depending on what time zone you're in. Looking forward to this Tech Talk today. This is going to be different than it's kind of out of my line of expertise, but nevertheless, it's very important. So we'll give a few minutes here, just a minute or two to for everybody to join that's going to, and looking forward to the topic today. In the next one, I'll talk about the next one at the end also, but the next one we're going to have a round table with a friend of mine, a senior IP engineer from Prescene. And so if you remember a couple of presentations ago, I ended up with a slide talking about the full meal deal when it came to quality of service. And so we're going to go and go to the next slide from that one on, and we're going to talk about implementation of that full meal deal. Anyways,
so that sounds awesome, Dave. Just a quick reminder, everyone that's here, if you have any questions for Dave along the way, please use the chat window for that. You can find that at the bottom middle of your screen. You can pull up that window and ask away. Otherwise, Dave, the floor is yours.
All right. It's great to be here this morning. And we're going to talk about, as the title slide says, we're going to talk about IPv6 in wireless networks. I thought that this would be a timely topic now with CN Wave coming, the Telegraph product coming, and that is solely IPv6 based. And so it's a good idea to have a little primer on that. This is not meant, by the way, to be an exhaustive study on IPv6. As I was learning how the protocol works, and I had to download a bunch of books and some white papers and then kind of go through the information, and then I took my lab, as we'll see here as we're going along here, and I implemented it in my lab. And so we have some examples at dual stack deployment in Cambium 450, in the Telrad LTE, in CN Pilot, and Cambium CN Pilot Wi-Fi. Anyway, let's get started. All right. So from a broadband operator's perspective, of which I include myself in that as a supplier to broadband operators, IPv4 addresses are running out. When people go to Aaron and ask for address space, sometimes they're denied. Sometimes they get a /24 256 host addresses, and so it's quite difficult. NAT has become the address conservation mechanism. Was not really designed for that in the beginning. It was meant to take many private IPv4 addresses and connect them to one public IP version address. But what NAT has unintentionally done for us is it's taken and been able to free up some public space. There are some challenges with doing wide-scale NAT. One of them I ran into a couple of weeks ago. An operator was using carrier grade NAT and had a few hundred CPE that were connected to a public IP address. They had a denial of service attack on that public IP address and took out those subscribers, all of them. And so it took some struggling with the firewall and to stop the denial of service attack, and then finally they did, and so that's one of the challenges, is that the firewalls that we need to maintain our networks are becoming more and more complex all the time, and so again, yeah, it's a challenge. So this month we're going to concentrate on IPv4 and IPv6 dual stack operation in wireless. Since that's my bailiwick, that's where we'll go. All right, so let's compare IPv4 to IPv6. So IPv4 is a 32-bit address. The broadband equipment bridging routing process is very well known. It's been IP version 4, of course, has been around for a very long time. Proposed in the 80s and adopted in the 90s, and so most broadband wireless access systems use routing or NAT combined with subnetting. Services like dynamic host control protocol, firewall, firewalls are well known, port forwarding, masquerading, lots of different subsystems are in use, well known, and default configurations in a lot of equipment. IP version 6, whole different ballgame. It is 128-bit addresses instead of 32-bit addresses. There's IP version 6 greatly simplifies IP addressing in that every device on the network, whether it's an IoT device, a CPE device, a router, whatever it is, can have a public IP address now, because this address mask is so huge. Subnetting is accomplished at the device level. Typically, every subscriber might have, whoops, I got 264 addresses. That should be a /64. It might have 64 bits addresses. We'll get into what the prefix and that looks like. There are two modes. There's a stateful and a stateless mode that it operates in. We're going to talk about the stateless mode here. Stateful mode you want to use when you're using a DHCP server, an IP version 6 DHCP server, and handing a prefix or addresses to a particular device. But IP version 6's real strength from a network point of view is the fact that in stateless mode, it uses a process called SLAC. We're going to talk about that, where the address is automatically delivered to the or defined in the end device, and it's going to be globally unique. And there can be many addresses. There's usually one global unique and one temporary, and then there's a link local address that's kind of derived in the same way as a MAC address. We'll talk about all of those things. All right, so here's how the IP version 4 addressing scheme, the 32-bit addresses were made up, right? There were 4 octets. And these 4 octets were 8 bits apiece. And so in total, we have 32 bits worth of information. Each octet was a decimal ranging from 0 to 255. So there were 256 possible combinations in each 8-bit group. The networks were divided into subnets from /8 to /32 for various purposes. We all have subnetted IP version 4 networks before, and right down to the point where we've got one address on 2 ends of a link at a /32, or we're dealing with large scale networks with typically in my world, in LTE, the largest network I've ever worked with is a /19, and of course on the webinar here, I'm sure that I've got network people that are slapping their head right now and saying, well, what do you know about this? But anyway. And inside of this, there are certain networks are non-routable, so private IPs. We're familiar with those, the 192.168 networks, the 172.16.31 network, and the 10. network. And it's all according to IETF standards. So we can look them up. You can see what this is not, again, not meant to be an IP lesson, but it's just, this is how IP version 4 has been put together. Many /8 subnets are reserved by governments and large organizations, which limit the number of public addresses available. This is this was one of the problems that was talked about. I can remember first seeing network administrators discuss this back in the late 90s, actually, was the fact that that many /8s were not available for public addressing. All right, so IP version 6, like I said, it's different animal altogether. Now we're talking about 128 bits. They're grouped into 16-bit groups represented in hexadecimal. So therefore, the numbering scheme goes from 0 to F, and so the addresses are defined like you see this example that I've got here. The first two terms of the IP version 6 has the same number of IP addresses as all of IP version 4. So what that's just I could have put the number of addresses down here. It's a huge number of addresses. Doesn't mean anything to most people. I want to take and talk about how we can use this mechanism in broadband wireless. So in my lab here, I want to talk about what we're going to see for examples here. My ISP delivers me a /56 bit prefix. So you can see here that it's going to have 3.5 terms here in the as far as my prefix goes. And the IETF, as you're going through the standards, they're recommending that we deliver a /64 to each subscriber. So that gives us a huge amount of address space for every subscriber, for every device that they connect to the network, for example, or every subscriber that you connect to your network. This is just a new freedom in addressing. So that's what the examples are going to show here. Okay. So let's do a little bit of defining and look at some of the documentation conventions that we have here. Let's start off with the link local address. Every interface that is IP version 6 enabled will have a link local address that's calculated for it. Addresses always start off with FE80, and then they can have some or all of the terms that there are when you're on a computer of some sort, be it Linux or be it Windows. The link local address will be attached to an interface, and you'll see that as that % and an interface ID that's behind it. So if I had a number of different interfaces on my computer, let's say I've got a Wi-Fi interface, I've got an Ethernet interface, and maybe a couple of virtual interfaces for some containers that are maybe running other software. I can have a number of different link local addresses, and they're all attached to a different interface. This link local address is unique. It's actually derived from the MAC address, and so there's a mathematical relationship between the two. As a side note, the default gateway is the link local address of the router's IP version 6 interface. So you see in my example here, which happens to be my surface at when I was doing this, putting the slides together. I have a IP version 6 address that we see in that second line. I have a temporary address, so I have a different one that the Slack has purposes for. I have a link local address that is on a particular interface. Then I have an IP version 4 address. I have an IP version 4 subnet mask. You can see it's a .248 subnet mask or /28. And then I have my default gateway, which is the link local address there of my router interface that is facing my surface. In any IP version 6 address, whenever we see 2 colons together, that means that the terms that are missing there are all zeros. So since the IP version 6 address is always the same number of terms, when I see like this link local address for my interface, I see, 1, 2, 3, 4, 5 terms that are here. That means that 3 terms are missing. So there's 3 sets of zeros that are missing in there that are represented by those double colons. When I see, you'll notice that in the IPv6 address, that I've got a few terms that are not 4 hexadecimal digits long. There's 3 of them that are 3, which I've highlighted in green. What that indicates is that the leading 0, or the most significant digit, is a 0 in that, and you can drop the 0 off. So when I see an IPv6 address of 2001:56A, like it is there, that means if I wrote it out in longhand, that would actually be 2001:056A. And as I mentioned before, the % which I've highlighted in blue, is the interface ID that's actually implemented that address. All right. So in this slide, if you want to take a copy of the screenshot of this, and blow it up if you need to. I've got a lot of information on here, but I wanted to show that that in my lab here that I've got a dual stack setup. I'm using a MikroTik router as the center of my universe, simply because it's really convenient to configure and have these functions run. So if we go from the upper left-hand corner there, that gray box is in fact my ISP's router that is sitting here. I have a fiber service, fiber to the home service in my lab, and so then I have a prefix that is an address that is assigned by my ISP, which happens to be Stateless here in Calgary, and so from that, we derive a bunch of information. I have that running in stateful mode, meaning that the DHCP server in my ISP's router is going to deliver a prefix to my lab router. I have a lab router connected to a particular port, and I have an IPv6 DHCP client that is running, that is looking for that prefix. And so the prefix that you see here is that 2001:56A77849F. And 9F9, in fact, is a /60. I'm taking a /60 address out of this. They are giving me a /56-bit prefix. That means that that I can have a number of DHCP clients that are connected to my ISP's router, which will each deliver a unique prefix to each of these DHCP clients. In my case, in my lab, I've taken and asked for a /60. So I can take I have 16 networks that I'm able to generate prefixes for with this combination. So what I do with this in IPv6, the DHCP client is not an address as it is in IPv4. It is this prefix. This prefix I park in a pool. So I create a pool, which I've called DC Office here, that you can see there, the second, the IPv6 pool portion here, and there is my prefix in that pool. Now my prefix length is 64 bits in here. I've been delivered a 60-bit prefix, so that means that then I can have a number of prefixes that are generated off of that. So what I've done is I've taken and applied, requested an IPv6 address on a number of interfaces on my router. So you can see on the info column here of the IPv6 pool used prefix box here, you can see that I've got this LTE layer 2 PDN, I've got a VPLS PDN, I've got a network called DC Desk, which happens to be all my office stuff. I have another layer 2 PDN, which all these LTE layer 2 PDNs belong to Telrad. I have one called Ether 7. That one is, in fact, the interface that is going to my Cambium 450s, my Cambium 820s, my Cambium CN pilots, and so on. Then I have another one that I call Stateless Bridge. When I want to take an IP address, version 4 or version 6 from the Stateless router, I have it sitting on the bridge, and then I simply connect to the bridge and I propagate my data away from that bridge. Use it for a couple of different things. I also have one more on a port called Ether 15, and so a number of addresses that have all been derived from this pool that I was delivered. And at the same time, I have IP version 4 running from the Stateless router into my lab router, and so I have a DHCP client that is receiving an address from 192.168 address from my Stateless router, and then I have that divided up into a bunch of different networks, and so I have DHCP servers configured for those, and then you can see down in just above the MBSI Wave logo here that I've got quite a number of devices that are in my lab that have an IP version 4 address that are running at the same time as the IP version 6. Quite a bit of information there, and this took a bit of time to figure out how to do this the most efficiently. But when I did, when I started using Slack, and from my router's perspective, my lab router's perspective, propagating IP version 6 addresses with a prefix and using the stateless auto configuration feature of IP version 6, it turns out to be a pretty seamless operation. Now, all right, so let's start off here with some of my configuration that I have here. All right, so first step here is my Cambium 450 point-to-multipoint network. In this case, I have a 450i access point talking to a 450i configured as a subscriber module, which is connected to a Raspberry Pi. And this is through a CN Matrix 2010P switch. So the switch is powering the 450 access point, and that is connected to that Ether 7 on my MikroTik router that I'm using for my lab functions. So while the 450M has IP version 6 capabilities, I'm not using it. I'm only managing the 450s and the CN Maestro switch with IP version 4. But I've connected the Raspberry Pi, of course, to the output of the Ethernet jack of the subscriber module. And when it connects to my router, lo and behold, because I have an IP version 6 enabled interface here on Ether 7, it through Slack on Ethernet 0 here, you can see that I have both an IP version 4 address and I have an IP version 6 address, which I've highlighted in red. It might be a little tough to see. I shouldn't have used red, maybe another color. But anyway, there's the address for it, and so the prefix, of course, you see the 200156A7784 9F, which is my 56-bit prefix. 94 happens to be my 64-bit prefix, and then the 3919 and all the rest of the address, the last 64 bits of the address are derived using this Slack process inside the Raspberry Pi itself. And it has a link local address of that FE80, 30s, D9, AE, so on. And that's the physical link of Ethernet 0, of Ether 0. So if this makes any sense, my Wi-Fi is not turned on at the moment, so of course there's no address there. And loopback in Linux is always just an IP version 4 address. I would have to take and configure a loopback address, but in Internet 6 here, it says that it's all zeros with a 1 on the end is the Ethernet loopback address here in Linux. So there I have you have what a dual stack configuration looks like. It's sitting on the end of a 450 network. Very, very popular, very common, and we'll see in a minute here some of the things it can do. All right. All right, so CN Pilot now, they participate in the stateless auto configuration. So I have my CN Matrix 2010 that is powering my E430. My E430 is my Wi-Fi here in my office. And you can see that it has both an IP version 4 address, but CN Maestro reports the IP version 6 address. And so that details box that I have there, that is from the configuration panel in CN Maestro. I can click on that 200156A7784 address, and I can log into the GUI of my CN Pilot, and just as though it were an IP version 4 address, away it goes. You can see that I'm running software version 4.1.1. I can update that. There's one newer one that's 4.1.3 or something like that, but not. And so the in-sync indicates that the configuration in my Cambium access point here is synchronized with the configuration in the AP group that I've got configured in CN Maestro. So the overhang, the box beside here are the 2 clients that were connected to my access point when I created the slide deck. And so you can see that both of those clients, one happens to be my BreezeView server for my Telrad, and the other one is a Raspberry Pi that is sitting on a drafting table that I have here in my office. And you can see that both of them are dual stack. Both of them have an IP version 4 address. They have an IP version 6 address, and of course the CN Maestro knows what SSID they're connected to. It knows what operating system it looks like it is, what band it is, all that good information. If I scrolled across that, of course, I'd see the signal strength and quality and how much data has been used and all those kind of features. So whether it's IP version 4 or IP version 6, I have all of this functionality available to me in my CN Pilot Wi-Fi. All right. So now I've got my Telrad LTE network. And I could probably have done this with any network that offers a layer 2 bridging. In Telrad's case, I wanted to show this off because it's a little bit more complex to set up and to maintain than what it is. The system itself, for those of you who have been on one of my LTE, my Telrad LTE courses, you know that the layer 3 PDN in Telrad's LTE system right now is only IP version 4 capable. It is not IP version 6 capable yet. The CPE 12,000, which I have here, has a feature in it that will enable IP version 6 in the WAN IP addressing scheme, but currently that functionality is not enabled. So all I have available to me on my WAN side of the CPE, that is the connection between my CPE and through the base station to the EPC, is I have only IP version 4 functionality. I want IP version 6 at my customers. How do I do it? So what I do is I set up a VLAN in an EPC, a layer 2 PDN VLAN that I can put my IP version 6 service on. So I have it connected to an interface in the router, and it's one of those interfaces that we saw a few slides back that is IP version 6 enabled. So there I have it. I have IP version 6 appearing at my my layer 2 PDN, my particular layer 2 PDN, which happens to be a VPLS in this particular case. Now at the CPE, I have to take the CPE and not have it run it in NAT mode, but I have to take and run it in layer 2 tunnel mode. So we see here the configuration parameters that I've enabled in the CPE in order to do that. So I need to have first of all, layer 2 licensing in the EPC, which I do, and then I can set my CPE in tunnel mode and increase the WAN MTU to 1600 bytes. It's going to be a GRE tunnel, as you can see here in the configuration, that gets created between the CPE and the EPC. I don't mean this to be an LTE lesson, but I want to explain this this in some kind of detail here. The CPE addressing, you can see here from the box that I've got sitting here, the WAN IP setting, is that it received an IP version 4 address. So I'm delivering this through DHCP relay through the IP version, the layer 3 PDN. When the CPE connects, it by IP proxy receives this IP address and this version 4 IP address from my my enhanced packet core. But in tunnel mode, what this means is that this GRE tunnel now is configured right across the network, right from that VLAN I was talking about in the EPC, right through to the Ethernet jack of the CPE. So now I have this layer 2 connection that runs right across the network. This makes the Telrad network look like the 450 did here in our 2 slides ago. And when I plug my my Raspberry Pi into my Telrad CPE, the address that I get, the addresses that I get given are highlighted in yellow there, so we can see Ethernet 0. And you see that I have a 10.30.2.22 IP version 4 address, which I've got a DHCP server configured on that same VLAN, that layer 2 PDN VLAN. And then also, since I've enabled IP version 6, you can see that I've also got my prefix, which is now the fourth term is 9F93. So I've used 90, 91, 92, 93, and actually I use a couple more of my my 60-bit prefix, my 60-bit prefix that I've subnetted to 64 bits, and then the Slack process generates the rest of the address, making sure that it's globally unique. And so I have IP version 6 running at the same time as I have IP version 4. And there you can see on my link local, my FE80, and I have a /64 prefix that is connected to that link local address. So I have my physical connection, the link local. I have my virtual connection, the INET 6 address, and my Raspberry Pi is running in dual stack. And so we'll see that in a second here. I'll do a little demo and we'll bring this up. So one of the things that I like about this is that when we run our equipment behind the CPE in this dual stack mode, that all of the normal tools that we're used to are all available to us. So in the first example here, I pinged YouTube, and so because I've got an IPv6 enabled, IPv6 server responded to me. And so you can see this is over the LTE network. So you can see that that I've got this IPv6 response from a ping that I sent to YouTube.com, which got through DNS got resolved to that 2607 F8B0 address, and it answered. I can do the same thing in IPv4, which is the second here. So I took I did an IPv4 ping to YouTube, and so it came back with its IPv4 addresses, a traceroute, I should say, not a ping, a traceroute to answered back with the hops necessary to get to YouTube from my lab. And then in the finally at the bottom here, I did a trace route using IPv6. So I just added the -6 command to the end of the trace, or suffix to the end of the traceroute command, and it came back in IPv6. And so you can see the nodes that it passed through, the routers that it passed through in order to get to YouTube and respond. So all of that worked exactly how I expected it to work. One of the things that, of course, with IPv6 addresses, is much more difficult to memorize. I suppose if you work with the prefix all the time, that's not bad. That's only 4 terms. That's kind of like remembering, in my case, anyways, with a /56, that 64, I should say. That's 4 terms. And so you probably can remember that, but all 8 terms of the address, very difficult to memorize. At this moment in time, because I'm doing some other lab work and stuff here, I've got a firewall enabled in my Stateless router, but not in the rest. If I were doing this as a production network, I would have my IPv6 firewalled in exactly the same way as I would the IPv4. I would not allow any conversation to begin from the internet coming into my network. I would drop all those frames and you know, then only cut holes through the network with the services that I want to connect from the outside network. Perhaps maybe VPN protocol of some sort, maybe layer 2 TP or PPTP or whatever it happens to be, and you know, just a few of those kind of things that I would want through. So I would configure the firewall exactly the same for version 4 or version 6 for exactly the same functionality. So let's for a moment here, let me just let me just go here and drag this down into here. Let's SSH pi at 172.29.128.75 for example, and so we'll go password is all right. So I'm logged in. So if I do an IPA from this this particular Raspberry Pi device happens to be there, you can see that my Ethernet 0 has all of the components that we talked about already: MAC address, IP version 4 address, and as well as an IPv6 address and a link local address. If I just we can repeat the ping. So there we have it. So in this case, my YouTube is responding with an IPv6 address because I've asked it to. If I there, I can respond with IPv4 if I want to, and so as I surf the internet, as I go from service to service, you can see that whether I need IPv6 or IPv4, I have both services available to me, and more as time goes along here. There's going to be fewer and fewer IPv6 to 4 tunnels, and more IPv6 native services across the internet. And so I think it's important for us in the fixed wireless world to be able to offer dual stack as a service that will just help our subscriber experience. All right, one last slide that I thought was interesting here. All right, so if you're taking your ping Facebook, what they've done with their IPv6 address, they've customized it. They've taken and customized their static IP address. So you see that what they've done is they've actually embedded Facebook into the address using hex. So there's no K in hex. So of course it has to be C, and there's no O, so it has to be a 0. But there you have it in the middle of the address. They have Facebook, and so once we get used to working with IPv6, it opens up many doors for us to provide services, to take and to deliver a better subscriber experience. I guess that's my point that I want to make here through all of this. And for some of us who have this may be our first brush with IPv6, I want to tell you that once you get used to it, it's not that difficult. And as time goes along here, I had this conversation with my friend from Preseam, and they're working very diligently to get their product ready for IPv6, as are many of the other common services that we're used to using. And so my point is that dual stack is possible, even if the system that you are trying to deliver the service over may not support it directly. That's the beautiful thing about this. So that's really today, 45-minute session, not bad. And next month, as I mentioned at the beginning, we can look forward to a little roundtable. I'm going to have Jeremy Austin, who is the senior IP engineer for Alaska Communications and with Preseam Networks, is going to be my guest on here, and we are going to take and discuss that full meal deal of QoS management over a wireless network, and perhaps we'll take a look at some of the points raised in Preseam's quarterly report, and talk about ways that we can take and increase the performance of the network that we have. And there are ways that we can do that. And of course, here at MBSI Wave, we are all about getting the most out of your equipment that you can. And of course, if you have any questions, any comments, any topics, simply send an email to marketing@mbsiwave.com, and Nicole and I will go through those. I will answer them as best I can. And if you have suggestions for Tech Talks in the future, please send them along the way, and we'll do our best to accomplish and deliver the topic that you're interested in. And want to thank you for your attention today. Have a great day, everyone.
Thank you, Dave. We'll see you on the next one.
Bye, everybody.